as we just said, this modified BFS algorithm, okay, by remembering predecessor information, we can recover not only the shortest path distance, but also shortest paths themselves from the source to the to a specific node. Okay, and you can also think that output this predecessor information actually give you something called BFS trees. Okay, sometimes this is also called BFS shortest path trees. Okay, in particular, okay, this BFS tree is associated to a source S. Okay, it simply consists of all the edges connecting the predecessor of between a node and its predecessor. Okay, and you can think that in terms of the tree, okay, the predecessor of the node is its parent in the tree. Okay, there's one node which doesn't have a predecessor, that's a source node, and that's the root of this tree. Okay, we're going to see an example in a minute, but in general, you're probably all familiar with trees. Okay, what is that? What are trees? A so-called free tree or just a tree is simply a connected graph where there's no cycle. Okay, alternatively, it's a connected graph where the number of edges equal to the number of vertices minus 1. Okay, the one property of the tree is that given any two nodes in the tree, because there's no cycle. Okay, so for example, this is a tree. Okay, because there's no cycle, given any two nodes, say this node and this node, there can only be a unique path connecting, unique simple path connecting them. Okay, now a rooted tree has a root basically, and let's say that suppose this is the root of the tree, and then where all other root nodes in the tree, other than the root itself, they have a parent which indicates the tree structure. So for example, if this is the root, let me make the green dot here, then the parent of, let's call it U, x1, x2, x3, x4, x5, x6. Then the parent of x2 is U, the parent of x3 is x2, the parent of x4 is x2, and so on. Okay, so now note that once I know the parent, who is my parent, then the tree is completely decided. Okay, because that to go to the root, you can start with any node by following the parent pointer, then you can go to the root. Okay, so the edges connecting a node with its parent will basically give you the tree back. Okay, and in the case of the breadth-first search, as we said, we're going to take this the root will be the source node itself. Okay, then we take the collection of the edges between a node and its predecessor, namely its parent. Okay, then since everyone has only one parent, this would give us a tree back, and this tree is called a BFS tree. Okay, all right. Now, in the example that we went through earlier, a few minutes ago, actually, we already saw that tree, but let me just draw it here again and show the tree, take the tree out separately. Okay, so remember in this example, if we start with the source S, and remember that the way that we perform BFS is that we always, when we explore a node, its neighbors are always explored in increasing order of their labels. Okay, lexicographically. Okay, so using this convention, okay, then I'm going to mark all the BFS predecessor in red. Then the predecessor for A is 1, is S. The predecessor for C is S as well. So the predecessor for A is S, that gives me this edge and this edge. And the predecessor for E is A, and the predecessor for B is E. Predecessor for G is C, and the predecessor for H is also E, and the predecessor for G, for I is G, and the predecessor for F is G. So now, if you look at the set of red edges, okay, let me just draw it out as A, C, G, I, F, E, H, E. We see that we have a tree, okay? And also remember that what's the shortest path distance to this node? At S, the short path distance is 0, this is 1, this is 2, and this is 3. Okay, now you see that this tree, actually, intuitively, what happens is that in this, this is the BFS tree with respect to node source S. Okay, so this is the BFS tree rooted at S. Okay, and as we see that basically in this tree, you can think that all of these nodes has layers. Okay, and their distance in the tree to the source are exactly their shortest path distance in the original graph. Okay, because this is not surprising because the unique path from the root to each node actually give you the shortest path from the root to that, from the source to that node. Okay, all right. So in other words, I'll add this to the slides later, but let me just write down the claim here. The path from the root S to any node V in your graph, okay, is a shortest in the BFS tree T. This is our BFS tree T, okay, is the shortest path from S to V in the input graph G. So this is input graph G. This is our shortest BFS tree T. Okay, so the path in this tree is exactly encodes shortest path in the original graph. Okay, and the reason, as we said, is because all these edges encode parent information. Okay, so for example, what is the meaning of S to A and A to E? That meaning is that from E, there's the shortest path along which my predecessor is A. Okay, so in other words, this AE is in the shortest path leading to E. And then by the same argument, from A, there's the shortest path to reach A with the predecessor S. So SA is the shortest path to A. And then you find the shortest path to A plus the AE that finds the shortest path to E. Okay, this is what this tree is encoding. Okay, all right. So this tree can themselves be useful, okay, once we remember this predecessor information. Okay, all right. Okay, of course that when we, this is just exploring the graph starting from a single source node. Okay, note that recall we said that if not all the nodes are reachable from S, then this will not explore the entire graph. Okay, so in general, to explore the entire graph, we need to run the full BFS algorithm. Okay, and now this would the output of this will be, instead of one BFS tree, this would be a BFS forest, what we call, namely a collection of BFS trees, one for each collection of BFS, consisting of one BFS tree for each component connected. In the graph. Okay, so for example, if we run BFS over this graph, then the output essentially will be a BFS tree. So the blue edges are the output BFS tree, okay, for this component. And then depends on where's the root, we're going to have a tree here and another tree here, okay? So this three tree will be the output, which form a BFS forest. Okay, so what we said so far is that we talk about the so-called breadth first search algorithm. Okay, this essentially is the way to traverse a graph, and as we mentioned earlier, it would visit all the nodes in the graph once as well as all the edges in the graph at least once. Okay, those is the we check all the edges when we explore. For every node, we explore all the outgoing edges going out from it. So in the end, we will touch upon every edges exactly once for directed graph and exactly twice for undirected graph. Okay, and it takes time proportional to the size of the graph, which is size of vertices plus the size of edges, V plus E. Okay, but it has the additional property that because we always, when we explore those pending nodes, we always explore those in order of their first discovery time. Okay, so it turned out that we're essentially exploring all the nodes in order of their shortest path to the source. Okay, so this can be used to as a byproduct to compute the shortest path to the source. Okay, so it visit all the nodes kind of in the wavefront. First, to visit all the nodes at distance 1 from the source, and those are stored in the pending. And then you add those distance 2 from the source. Those are added to the end of the pending list. You will only process them after you process all that distance 1 from the source, and so on. Okay, and because of this wavefront propagation, you can imagine that at every node, you go as wide as possible to see whoever you can reach just with one step. Then at the next layer, you go as wide as possible to see who all the nodes I can reach within 2 steps. Okay, that's why it has the name breadth first, because you go as wide as possible to see who you can reach just at this moment with one more step. Okay, so that's why we call this algorithm breadth first algorithm. Okay, the key message to remember is that it's effective graph traversal graph search algorithm take time only linear to the size of the graph, which is the number of edges plus number of vertices. Okay, and it has the byproduct that it actually visits all the nodes in increasing distance to the source, and it can be used to compute the shortest path distance from the source to all other nodes.